Please welcome Krister Sham. Hey, Krister, what's up? What are you going to talk about?
So, Jay, I work here as a physicist at the
Right.
University of Waterloo at the Institute for Quantum Computing, and I'm an experimental physicist. I do experiments. Now, the type of stuff I study is light, and in particular, the tiniest little particles of light we call photons. And Martin, he just came in and gave us this great explanation of how quantum superposition works and how you can do that with light. But for me, the thing that gets me excited is something we call quantum entanglement. Now, when two things, say quantum particles like atoms or electrons or photons, when they become entangled, they share these really strong correlations with one another.
So how do things get entangled, though?
Well, to entangle things, they have to come together and interact. And what I mean by strong correlations, because, well, I'd like to demonstrate something. I've got two tunies here, so I'm going to give you a tunie, Jay.
Okay.
Don't spend it all at once.
It's a profitable evening already.
So with this coin here, if I were to flip it, I could either come up heads or tails. And what did you get?
Tails.
You got a polar bear, I think, with the tuning. Yeah, so we...
It's called tails.
Tails, sorry.
Physicists.
So if we flipped our coins, sometimes I get heads and tails, sometimes you would get heads and tails, but we wouldn't expect to always get the same result. But if these coins were correlated with one another, then every time I got a head, Jay would get heads. And every time I got tails, Jay would get tails. So that's what we mean when we're talking about correlations. You can keep the tuning.
Actually, I put it right. But so I'm still not sure how things get entangled. Like what has to happen?
So how we do this in the lab is I take these two photons together and we interact them. And usually what happens is when you want to interact things, you have to take quantum objects and interact them somehow. And so that's what we do is we take these photons and we interact them, and they become so strongly correlated with one another, much stronger than anything that we ordinarily experience, much stronger than these coins. In fact, it's so strong that this kind of very interesting connection develops between the two. You could take them very far apart, and they would still maintain these correlations. Einstein, he called it spooky action at a distance, but it's not really that spooky to me. In fact, it's quite exciting because we can base a lot of our new quantum technologies on it, like quantum computing.
So, but interacting, like we're interacting?
Kind of, I guess. It's not, I mean, we'd have to be quantum objects for that to happen, but yeah, in a sense, like how we're interacting.
But wait, we may not be quantum objects, but this is a quantum band. They are called the qubits.
Yeah, but I'm not 100% sure. Like, how would that actually...
I think I got it. You better make some room. I'm coming to get you.
Wait, Jay, what's going on?
Yeah, like this, right? Okay.
Sure. Jay, I don't know what kind of band you brought, but that's not exactly how we do this in the lab.
That was a little bit of superposition as well
Yeah,
as entanglement.
I think so. So I'm not sure that really makes, I'm not sure that makes us entangled.
Well, I actually think that we can make this work, you know?
I'm not sure I follow.
Well, why don't you, if you don't believe that we're entangled right now, well then...
Never seen this in the lab before.
Oh, yeah? Watch this.
Rob. Oh,
Jay.
yeah.
Jay, what's
That's
going
right.
on? Jay, what's happening?
Okay.
Okay, I take it back. Einstein was right. This is spooky. Jay, if we're really entangled,
Yeah?
then you have to understand that this works both ways.
Oh, yeah, go for it.
I think we could have some fun with this.
I think we could have some fun with this too. Mr. Sham.